Super. So,
Great. Okay, let's get started right away. We only have 20 minutes. Welcome. This is a very complex topic.
bildgebendes Radar.
It's about imaging radar, and more specifically, it's also about the physical limitations of radar.
Probleme von Radar. Und ich will ein bisschen
I'd like to explain, or rather show, what we and our colleagues at the university are researching to overcome the resolution limitations inherent in radar physics.
als Physik selber hat.
That's exactly where we'll begin.
Steigen wir jetzt ein. Wir kennen natürlich alle.
Of course, we're all familiar with the challenges we increasingly face, especially in outdoor environments.
Das heißt,
We're talking about industries such as ports, agriculture, and railways, all areas that are highly relevant to us.
ist ein Thema, das uns sehr berührt. Wie kann ich Infrastruktur
The key question is, how can we monitor infrastructure in real time under harsh environmental conditions? And we've all experienced it, driving across open landscapes in summer, for example the Magdeburg Plain, where you can suddenly enter a cloud of dust on the highway.
Staubwolke reinfährt. Jedem, dem das schon mal
For
passiert,
anyone who's ever experienced it, fog is nothing compared to this. It's truly pitch black. And of course, it quickly becomes clear that optical sensors simply aren't sufficient in these conditions.
auch im Landwirtschaft
This is especially true in agriculture, where the future is full automation. That means we need solutions that work 24/7 under all conditions.
und dementsprechend.
And that's exactly what we're talking about here.
Wir haben dann gesagt, ich kriege oft die Frage,
I'm
warum
often asked, why radar anyway? Why not cameras or high-resolution LiDAR? That's why we rented a hall at an automotive test facility.
Automotive von Audi eine Halle.
In this test environment, they can simulate real-world conditions over a distance of about 100 meters.
Bedingungen
This includes rainfall at different intensities, just as it occurs on the road. They can also generate fog. We then set up a camera. And as you can see here, I also have a laser pointer with me. You can also see the reflectors we placed as targets.
Sie sehen hier
First,
auch,
this is the camera image.
die wir einfach mal als Ziele hingestellt haben. Und ja, was man sieht, ist das Kamerabild.
As you can see, the weather is perfect. You can see everything clearly.
LiDAR-Bild
Next, we generated the corresponding LiDAR image alongside it, and you can clearly see the high-resolution result.
Danach sind wir hergegangen und haben einfach mal in der Halle.
Then we introduced fog into the hall. And as you can see in this short sequence, the camera view behaves exactly as the human eye would. The targets completely disappear. At the same time, the LiDAR begins to primarily measure the fog itself.
Nebel
In this situation, it becomes effectively unusable.
bringt
If
uns
this were an autonomous machine, it would have to stop because it would no longer detect the actual environment, only the fog.
Staub.
The same applies to dust and heavy rain. Under these conditions, you don't have a system that can reliably operate 24/7.
Man sieht hier noch mal ein Bild.
Here's another image, a bird's eye view of the hall.
Tiefe drauf
In the foreground, you can see the LiDAR at the exact moment the fog was generated.
entstanden ist.
At that point, we are essentially measuring the fog itself, the fog droplets in the air.
Wir sehen hierzu die
Here, we can clearly see the targets being detected by radar.
Radar hat
Radar is completely unaffected by fog, dust, and similar conditions.
Man sieht hier jetzt mal ein
Here's an image we captured in a parking lot. We placed two poles here, with a wall in the background. We're looking at this scene using a standard automotive radar system, the kind most of you are familiar with from your cars.
Auto.
It's used for functions like adaptive cruise control, measuring distance to the vehicle ahead, and maintaining the gap automatically. And with a conventional radar, you can see the following.
Automatisch sogar. Und Sie sehen auf
Actually, both images show this.
Bilder eigentlich
This one may be based on a slightly newer system, and that one on a slightly older standard. But in both cases, you get a relatively simple image.
Bildgebung. Sie haben ein paar Reflexionspunkte.
You see a few reflection points. You're looking at these two poles, but you can't distinguish them from one another. You simply see a reflection, say, from a vehicle, and the system can tell you there's an object ahead. So you need to brake because there's a truck in front of you. You see it simply as a reflection.
Nicht wirklich zufriedenstellend.
Of course, that's not really satisfactory if you want to create an image. The reason is that radar also has a fundamental physical limitation. Its angular resolution is inherently limited.
Ich schaue gerade mal zu den Kollegen von der Universität.
Let me just look over at our colleagues from the university. I'd say about 0.7 degrees is roughly the best you can achieve. So we arrive at a principle that is simply dictated by physics. If you want a high-resolution image, you have to make the radar correspondingly larger. You need a much larger antenna aperture. Just for fun, we asked a very expensive AI program to show us what the perfect radar would look like. That was very expensive. The AI was actually my daughter. She simply drew a car and said, "Okay, let's put a huge radar on top." And that illustrates the problem. With a huge radar, I can produce a very high-resolution image, but of course, I can't actually mount such a radar on a car. On a car, I need good aerodynamics, and I need a compact device. After all, nobody has an oil tanker parked at home where size doesn't really matter. So that's the challenge. On the one hand, high resolution means a large radar. On the other hand, we want high resolution with a small radar. So how do we achieve that in practice? This is a practical evaluation platform of a reasonable size. It operates at 77 GHz, the well-known automotive radar frequency that you're familiar with from modern vehicles. We mounted it on the side of a car and used a principle that has been around for quite some time. Most of you have probably heard of it, or at least seen it mentioned online. Satellites have been using this technique, known as synthetic aperture radar, SAR, for around 40 or 50 years. It works like this. As a satellite flies over the Earth's surface at a constant speed, it captures individual radar images. These images can then be stitched together to create a single, very high-resolution image. If you search for it online, you'll find impressive radar images of volcanoes, islands, and many other scenes, all in extremely high resolution. The challenge we identified was that SAR is a well-established and highly effective technology. Instead of building an enormous physical radar, you create a large radar aperture virtually. The catch is that, traditionally, you need a very long travel distance, typically a satellite or an aircraft. Our challenge was to make SAR work over short distances, for example in automotive applications, on locomotives, or on AGVs. That turned out to be quite challenging. About 6 years ago, together with our colleagues at the university, we started running the first experiments. We mounted the radar on this BMW and drove along a road near our facility. The resulting radar image was already remarkably high resolution. Here, you can compare it with the corresponding Google Maps view. This is a supermarket that we simply drove around once, recording individual radar images along the way. By combining those images, we created a radar image with a level of resolution that was not previously achievable with a stationary radar system. It was generated simply by driving past the scene, parked cars, and many other details. This work dates back about 6 years. At that time, however, the drawback was the processing time. The post-processing was extremely computationally intensive. The entire trunk of the BMW was filled with computers performing the calculations. Over the past 6 years, together with our colleagues at the university, we managed to miniaturize the entire system. Advances in hardware, especially powerful GPUs from NVIDIA, played an important role. Today, everything fits into a small box based on an NVIDIA Jetson module, so there's no longer any need to fill the entire trunk with computers. We also succeeded in processing the data in real time. That means you can now drive this vehicle and watch the radar image being generated live. This opens up entirely new possibilities for vehicles operating in outdoor industrial environments, locomotives, ports, bulk material handling, and anywhere else where dirt, dust, or harsh conditions cause optical systems to fail. In these environments, you can perform real-time infrastructure monitoring. Or you can combine radar with optical sensors through sensor fusion, providing high-resolution information from complementary sensing technologies.
Und Radarsensoren, die ähnlich hochauflösende Bilder geben. Wir haben dann noch eines gemacht, beziehungsweise
The next step actually came about almost by chance. I'll glance over at our colleagues again.
was passiert denn, wenn ich
Up to this point, our approach had been to mount the radar on the side of the vehicle and drive past the scene while collecting individual radar measurements.
und nehmen da diese Einzelschnitte. Das ist einerseits interessant, aber ich fahre ja vorbei.
That's certainly interesting, but in many real-world applications, especially in automotive systems, you also need a forward-looking radar for collision avoidance.
Das heißt, ich will natürlich auch nach vorne Antikollision machen und ich möchte auch dort eigentlich höhere Auflösung haben. Die Universität hat dann gesagt,
So our colleagues at the university asked a simple question. What happens if, instead of driving past an object, we drive directly toward it?
aber die Theorie war,
The theory was that the radar's beam still has a sufficiently wide angular aperture. Even while driving toward the target, the side lobes of the beam still observe different viewing angles, allowing the SAR principle to work.
dann haben wir das auch mit dem Front-Looking SAR gemacht.
So we implemented what is known as forward-looking SAR, and the results were very exciting.
Fahrt einmal den Block mit dem Test.
After nothing more than a single drive around the block with the test vehicle, we were able to generate a highly detailed map. It was an initial proof of concept, but it clearly demonstrated that this approach can provide valuable additional information for future sensing systems. You don't have this in today's vehicles, not even with the latest standard systems. This level of side view resolution, where the system automatically creates a map of the surroundings, is something quite different. You can clearly recognize roads, entrances, parked cars, and many other details. And the key point is that it still works in fog. That's exactly where LiDAR reaches its limits. Of course, in clear weather you can achieve similar results with LiDAR, perhaps even at a higher resolution. But a vehicle also has to operate in Finland, or in winter, or during storms and snowfall. And that's where radar really shows its strengths.
Wir haben dann hier auch noch die Möglichkeit, das ist auch eine spannende neue Entwicklung, die wir
We now also have another exciting development, which is only about 1 or 2 years old.
mittlerweile.
Software is now available that can simulate radar.
Das hilft uns extrem mit dem
That has been extremely helpful when working with customers, because we can now, for example, simulate an application such as a tram.
Gerät nicht erst bauen und eine
We no longer have to build the device first and carry out a test drive before evaluating the results.
Applikation.
Today, there are simulation tools that allow us to define a radar configuration and simulate what the results would look like.
Wie würde denn
The simulated results match the real hardware with an accuracy of well over 90% once the radar is actually built.
Tour dann, wenn ich es dann tatsächlich draufbaue?
That helps us tremendously because before we even pick up a screwdriver and build a new radar system,
Nehmen und ein neues Radargerät bauen.
we can already determine which configuration a radar needs in order to achieve the desired performance.
Die Konfiguration muss so ein Radar haben, damit ich das gewünschte Ergebnis rausziehe. Ja? Und das kann dann
And the result can look something like this. Let me see if it starts automatically. Otherwise, we might have to.
jetzt läuft los.
There it goes. Here we've simulated a tram driving through an urban environment. At the top, you can see the automatically generated radar image for this particular configuration.
Das Radar wäre an der Seite von der Straßenbahn.
The radar is mounted on the side of the tram, so as the tram drives past the scene, we generate this image using the current configuration, which is based on a 2D antenna.
Also das ist nicht real.
Again, this is a simulation. It hasn't been measured in the real world. But we know with more than 90% confidence that if we install the radar on the tram using exactly this configuration,
Zu über 90%
the
ähnlich
real result will look very similar, if not virtually identical to what you see here.
hier zeigen. Und das macht das
That's what makes this so exciting.
bislang
Until now, whenever we worked with customers, for example, locomotive manufacturers, we first had to build a radar, test it in the field, go back to the workshop, make changes, and repeat the entire process.
neues
All of this used to take a great deal of time. AI, the latest software, and radar simulation tools now allow us to move much faster and keep pace with the speed at which industry is developing.
Das ist jetzt im Endeffekt
What you see here is essentially a piece of hardware and evaluation platform.
Plattform. Das haben wir benutzt für die
We
Simulation.
use it for our simulations, but we also use it with major customers.
Mit diesen
It's an imaging radar with 4 chips operating in the 77 GHz band.
70 Gigahertz-Bereich.
Customers can use it to record their first radar images and work with the raw data. We provide the data via ROS2. That's something most vehicle manufacturers appreciate because they're already familiar with ROS2. It integrates easily into their existing development environment, allowing them to process and evaluate the radar data using their own software.
Letzten Endes wird
Ultimately, this means we're already well prepared before a custom radar is even developed. The customer has already worked with the software and the data, and we've already completed the simulations. So, with a relatively modest investment of time and budget, we already have a very good understanding of what the final device should look like and what it is likely to cost. At that point, the customer can decide whether to move forward. The risk is much lower because the feasibility has already been demonstrated. They can simply make a go or no-go decision. That's a tremendous advantage, and one whose value really can't be overstated.
Genau, und jetzt können wir noch,
I think I still have 2 or 3 minutes left, so let's take a look at a few potential applications. As we've already seen, one example is trams, and the same concept could just as easily be applied to locomotives. The idea is to use SAR to continuously map the surrounding infrastructure. Take the example mentioned earlier. Deutsche Bahn operates around 33,000 kilometers of rail network, and all of that infrastructure has to be monitored somehow. Now imagine the Berlin-Hamburg high-speed rail line. As long as there's no construction work, I believe around 300 trains travel that route every day. Imagine every one of those trains being equipped with a side-looking radar. As each train passes by, regardless of its speed, it automatically captures a high-resolution radar image of the surrounding infrastructure. 20 minutes later, the next train passes and records another image. Now imagine combining all of those images. And if, in addition, you have an AI system in the back end analyzing the data for recurring patterns, then after a few months you might have 100,000 images of the same infrastructure. AI is exceptionally good at detecting patterns and identifying even the smallest changes. Going back to the landslide example I showed earlier, you could imagine a future in which the system detects subtle changes long before a landslide actually occurs. That capability doesn't really exist today. Yet, in principle, you could monitor an entire 33,000-kilometer rail network in real time throughout the year, and in virtually all weather conditions. This is something we have also achieved. For example, we recently received an award for this at European Microwave Week, and we are very proud of Teresa Nogel for her work. In one of our experiments, we also demonstrated that debris detection works extremely well with this system. What does that mean? Many of you may remember the Concorde accident, where a piece of tire debris was thrown up during takeoff, entered the engine intake, and ultimately led to the aircraft accident. That is every airport operator's nightmare, debris on the runway that can be sucked into an aircraft engine. These are the classic scenarios, of course. Another example is environments like waste handling systems where conditions are simply dirty. You would like to use sensors there, but optical systems are not practical because you would constantly have to clean the lens. That's exactly where radar comes into play. We were just discussing this with colleagues from the security sector. We've already received several inquiries today, and people are telling us they're seeing these challenges more and more often. Sabotage attempts, drone detection, and similar scenarios. Imaging radar can significantly improve monitoring capabilities in these areas.
Okay, good.
Right, we've already talked about agriculture. So there are dozens of applications from railways to steel production, ports, and many other outdoor environments. I hope this gave you a first impression of what is possible. If you're interested, we have a booth here in Hall 7A. Feel free to stop by. We can show you much more and discuss the topic in greater detail. I think it's a very exciting field. Thank you very much for your attention.